Alrighty, welcome everyone. On behalf of the Methane Guiding Principles, we are pleased to hold the first in a series of technical webinars. And today we're excited to hear about the methane research on remote sensing carried out by Dr. Sahar El-Abadi, the postdoctoral scholar in energy resource engineering at Stanford University. Without much ado, Sahar, the floor is yours.
Great, thank you so much, Chris. I will begin sharing my screen. All right, you all should see my screen in presenter view. Could I get sort of a thumbs up, Chris, if that's...
Yep, perfect.
Okay, perfect. All right. Hi, everyone. It's really sort of wonderful to be here today with all of you. Thank you for joining. Good morning if you're on the West Coast, but I'm really excited that we have folks from all over the world here. And I'm going to be talking about the work that I've been doing that's really quite a team effort that's been led at Stanford University over the past several years with Professor Adam Brandt, who's sort of the leader behind this venture over the last now 4 years, but really a whole slew of people have been involved in this. And I've sort of led our latest round of experiments. And I'm really excited to be sharing with you a synthesis of our work in evaluating methane sensing technology. And I'm going to be focusing on aircraft and satellite remote sensing technology. And I'll touch on a few other approaches as well, but really focusing on how aircrafts and satellites can help us rapidly find and fix methane leaks. So I think all of us here sort of on this call are very familiar with sort of the important climate change implications of methane, and oil and gas is a leading source of emissions of methane emissions, up there sort of with agriculture as well as other natural sources such as wetlands. However, oil and gas is really a target for mitigation at the moment because many of the largest emission sources can readily and cost effectively be mitigated. For a little bit of context, we are seeing methane leaks that are really larger than ever before. This is work, again, out of Stanford University by my colleagues, Yuanlei Chen, a PhD student at Stanford, and postdoctoral researcher, Dr. Evan Sherwin. And they analyzed an aircraft survey of the Permian Basin in the United States and found that sort of using aircraft measurements, the methane emissions that they were seeing are several-fold higher than official EPA estimates in sort of official government inventories. And again, sort of the work of Dr. Evan Sherwin continuing out of this, looking at several basins across the US, found that the key culprits for these very large emissions are a very small number of sites. And sort of in an analysis that's currently under peer review right now, he found that less than 1.5% of sites contribute up to 80% of total emissions. So while the work that I've just shared, sort of in Evan's work in this slide and the previous one, is very focused on the United States, and a lot of this work has been pioneered looking at oil and gas methane emissions in the United States, we don't really have reason to believe that this is different anywhere else. And so, you know, it's important that we sort of have more information and collect more data to shed light on the situation globally. But at the moment, sort of our understanding is that you know, we are underestimating methane emissions, and there are a small number of sites that are really the main contributors to emissions. And importantly, though, aircrafts and satellites can help us rapidly find and fix these large methane leaks. For a quick overview, very high level of these two technology types. So aircraft-based methane detection presents many advantages. It allows us for really rapid and widespread coverage. So aircrafts can conduct surveys over large geographic regions. The study that I mentioned that Evan conducted looked at sort of aircraft surveyed the entire Permian Basin. You don't require on-site access. You don't have to have an individual going site by site and looking at equipment as you would with many of the conventional methods for leak detection. And then because you're covering an entire large geographic region and all of the assets present, you have an unbiased sampling. Disadvantages, we can expect higher detection limits. You're measuring methane leaks from sort of flying several, potentially 1,000 meters above ground level. Some of these approaches, and I'll dive into this later in the talk, use a passive approach that depends on sunlight. So these approaches are weather dependent. You have to have favorable weather conditions for measurement. And finally, they typically will provide a snapshot in time where an aircraft conducts a survey on a given day and you understand what is happening at that moment. Satellites allow us to scale up this technology that's being used in airplanes to a truly global level. So this is one of the main advantages of using satellites for methane detection. They provide rapid measurement and regular repeated coverage as satellites return to the same locations at regular intervals in their orbit. However, now we're measuring methane not just sort of from several thousand meters above ground level, but sort of through the entire atmosphere. So you can expect even higher detection limits. And of course, you are constrained by weather limitations. We cannot sort of see methane plumes with satellites through cloud cover. And finally, satellites are very expensive to launch and to use. In today's talk, I am going to be focusing on sort of these three main questions. First, I will discuss how do airplanes and satellites measure methane? Next, I'm going to be diving into how Stanford and our research team independently evaluates airplane and satellite measurement capabilities. And finally, I'm going to share with you how do these technologies that we've tested, the aircrafts and satellites, perform in our tests. So to begin, I'll start by providing you all with the overview of how aircrafts and satellites measure methane. Methane absorbs infrared radiation. So this is the property that makes it a greenhouse gas. However, it's also the property that allows us to measure it using spectroscopy. And I'll walk you through how this works now. And the images on this slide show the wavelengths and the, particularly in the infrared radiation for which methane absorbs. So we have incoming solar radiation, which is reflected at the Earth's surface, and it is reflected in the infrared. If methane is present in the atmosphere, methane absorbs some of this outgoing radiation. So aircrafts and satellites, the most common approach that is used by aircrafts and satellites is to look at the differential absorption of outgoing radiation off the Earth's surface. So an aircraft will look at sort of the reflected sunlight and see that in certain regions, it is being absorbed at greater rates than others, and they will use this to calculate the amount of methane that is present for that region in the atmosphere. So as I said at the top of the slide, this is the most common technique called passive spectroscopy, and it's also used by all of the satellites. So it's most common for airplanes and what satellites rely on. However, there are a couple of other approaches that the aircrafts use. One of them is called active spectroscopy, and this uses the same principle of differential absorption of infrared radiation. However, here, the aircraft uses LiDAR to emit a beam, which is then reflected off the Earth's surface. And as the airplane travels, it then measures the differential absorption from the light that it emitted. So it's the same principle, but this allows us to overcome the weather limitations. For example, this can be performed on a cloudy day, as long as the aircraft is close enough to the ground. Finally, the last measurement technique that aircrafts will use and that we tested in our studies is called an in situ measurement technique. And this is a bit different. Here you have an aircraft. I've included on the slide a little intake port on the aircraft where scientists on the aircraft are continuously collecting atmospheric samples and measuring the methane concentration at a given point. The aircraft will then conduct a survey of a region or around a potential source, and then have a distribution of concentrations in order to backtrack a methane emission rate. So to summarize sort of the three main techniques that we see: passive spectroscopy relying on reflected sunlight. This is the technique that's used by most aircrafts as well as satellites. Active LiDAR spectroscopy, as well as in situ measurement. And so this brings me to the next portion of my talk, which is how does our team at Stanford independently evaluate methane and satellite measurement capabilities? So over the last several years, as I mentioned at sort of the top of the talk, this has been a really large area of focus for our research group, led in particular by Professor Adam Brandt, depicted on the slide here. But as I said before, this has been a team effort spanning many years, with several PhD students and postdoctoral researchers. We have a summary of all of the publications that have come out of our research group at the URL that I've included on this slide, and I'll reference many of the papers specifically throughout this talk. The basic approach that we use in conducting our tests is what we call single-blind testing format. So here this is an overhead shot of our field site from last fall, actually, in Arizona. We were out in the desert in Arizona, and we coordinate with the different operators that we're testing. So here I've depicted a potential aircraft that we would be testing, and they know the location. We coordinate with them in advance. They come out to the field site for several days at a time. And we conduct releases, but they do not know the volume we are releasing at. In fact, we don't even tell them whether or not we're releasing, and this allows us to evaluate false positives. So to make sure that they don't say that there is methane being released when there actually isn't. So just I'll briefly describe the equipment that you're seeing on this slide, but I won't focus too much on it, and I'm happy to dive into this more in the Q&A at the end. So here in this experimental setup, we had compressed natural gas that was released from these white trailers. These were all of our natural gas equipment was operated by a contractor. That's Rawhide, the logo, their logos displayed on the slide next to this equipment. And then you can see right next to the white trailers is a small pressure regulation trailer that drops the pressure of the compressed natural gas. And then you can see a small pipe. This is a corrugated metal pipe hose that leads to our release point here. And that's sort of our cloud of methane, where we are very precisely metering the amount that's being released, but the operator does not know how much is being released. Near the Stanford logo up on the top right of the image, that's our truck and our sort of canopy, where our field team, we were sort of sitting and conducting the tests and remotely controlling the flow rate of methane from a laptop at that location. And then this image on the right is what the release looks like using an infrared camera. So we test airplanes in this way, and then also sort of we time releases for when the satellites are overhead. So we know in advance when the satellite's orbit will be passing over our field site and conduct releases for the satellites. So between 2019 and 2022, we have conducted 4 different sort of campaigns, we call them, where we test anywhere from 1 to 20 different technologies. So we have conducted tests in California, Arizona, at both Ehrenberg, which is the location on the Arizona-California border, as well as Casa Grande in the center of Arizona. That's sort of right smack dab between Phoenix and Tucson, as well as tests conducted in Texas in the Midlands region. In total, we've tested over 23 different technologies, and our most ambitious campaign was the one that I led this past fall, which where we tested 20 different technology types, and we were out in Arizona for a total of 2 months collecting data out on a 4-acre plot, which is about 120 meters by 120 meters. And this is an image of that field site on the left of this slide. So across our tests, we have evaluated really every major remote sensing platform. So this includes 6 different aircrafts. I've included their logos here, and I'll share the results from those tests in the last portion of this talk. But Bridger Photonics, Carbon Mapper, GHGSat, Kairos Aerospace, Methane Air, and Scientific Aviation. We've also tested 9 different satellites, and I've included them here on this slide. And these range from sort of government satellites. Most of them are operated by governments. Worldview 3 and GHGSat, though, are both commercial ventures, commercial satellites. With the satellites, we work with sort of our different partners to collect the data acquisition from the satellite. So as I said previously, we know when the satellite is passing overhead. The satellite collects a snapshot, and then sort of we work with partners to obtain that data and then distribute it amongst our satellite analysis test participants. So those are depicted sort of on the right of this screen. So we have many different teams analyzing the data from the same satellite acquisition, which is quite interesting because you can see how different teams interpret the same set of underlying data. So we've had analysis conducted by GHGSat, researchers at academic institutes such as Harvard, Nanjing University, the University of Valencia, as well as private companies, and the Netherlands Institute for Space Research. So overall, the equipment that I showed on the previous slide allows us to conduct releases across several orders of magnitude. This is a ground shot of our metering and release stack. So in this configuration, we could conduct releases at 2 heights, 7 meters and 3 meters above the ground. So we can conduct releases across several orders of magnitude. This is, again, just an image of what sort of that plume looks like when an aircraft is passing over, and sort of they've colored the methane enhancements and then calculate the methane flow rate. And then here's a shot that actually I took from the field where we had 2 aircrafts that we were testing on the same day. And so they both happened to coincidentally be flying overhead at the same time. And there you can see that's what it looks like from the ground. We're looking up at the airplanes. In our 2021 tests, this was led by my colleague, Dr. Evan Sherwin, who I shared his photo on some of the earlier slides. We conducted releases using liquid natural gas, and this is a shot of what that field setup looked like. This was in Ehrenberg, Arizona, and using liquid natural gas, we were able to conduct releases actually up to 7,000 kilograms per hour. So almost 6 times what we were able to do when we're using compressed natural gas. And so this we really used for testing the satellites to see how they're able to see some of those even larger releases than what we're capable of. So before I dive into the results, there are a couple of limitations to our study design that I just want to address up front. First of all of the test participants, the aircraft operators or the satellite analysis teams and the satellite operations teams know the location of our field site in advance. This is for coordination purposes. It would be an incredible logistical challenge otherwise. And so as a result, they know exactly where to look in their images in order to look for methane enhancement, in order to look for sort of higher methane concentrations. And so as a result, this will sort of improve the performance on sort of lower detection limit. We can expect that they are able to see things a bit smaller than they typically would see if they were conducting tests sort of out in the wild. However, this doesn't affect their ability to quantify. So for example, to accurately estimate exactly how much is being released, it just improves their ability to find sort of the smaller end of the spectrum. Additionally, we really, wanted to maximize our ability to collect data and evaluate performance on sort of ideal conditions with a sort of a blank slate background. So the weather, as you can see from this photo, clear skies, moderate winds. And our geography was really arid desert, and we did our best to minimize potential confounding sources. So ideally, no other sources of methane, major sources of methane anywhere nearby. So keep in mind, as I'm about to sort of share my results with you, that those are sort of the limitations, and that also this doesn't necessarily translate to more complex geographies, and particularly not to offshore. That sort of would require a different measurement approach. So keep in mind, this is sort of land-based, and we did our testing in arid desert environments. All right, so this brings us to sort of the main part of my talk, where I share the results from our tests, where we evaluate how well these technologies are able to detect and quantify methane emissions. So first, just a note on how I'm going to be discussing methane emissions. So we find that using units of flow rate, so mass per unit time, is more informative. It really allows us to understand how much carbon is being emitted at a given time. So you'll see me using units of mass per time instead of concentration units, for example, ppm. Aircrafts, for all of the airplane plots that you'll see for those results, the units are in kilograms of methane per hour. In the satellite results that I'll share, we use units of tons of methane per hour, and that's a metric ton, so 1,000 kilograms. The way that I'll be presenting the results uses sort of two key plots that you'll see. So the first is a parity plot, and I'll walk you through how to interpret this briefly before I show you all of them. So on the horizontal axis, the x-axis, we have our metered release rate. So that's how much methane we know we are releasing. This example plot is for an airplane, so the units are in kilograms per hour. And then on the y-axis, the vertical axis, we have the fully blinded report by the operator for their estimate of methane emissions. So the dashed line across is the x equals y line. So the closer the points are to x equals y, the more accurate, the more close the estimates are to the ground truth value. And then in these figures, all the error bars you'll see will represent 95% confidence intervals. So here's the data overlaid on those axes. So each individual point represents a measurement. As I said before, so the x-axis error bars, those are 95% confidence intervals in our metered release rate. And then the y-axis error bars on each point represent the uncertainty reported by the operator. We include sort of the equation of best fit using ordinary least squares. That's the equation you see on the plot, and the r squared, sort of the r squared value of that best fit equation. So this is sort of an evaluation of how well the aircrafts are able to quantify emissions. We also, or the satellites. For the aircrafts also, we looked at sort of the probability of detecting a release, and this is on the lower end. So here on the x-axis, you'll notice the units are smaller. We're just looking at the lower release rates. And again, so that's that x-axis is the metered release rate. And in this case, on these plots that I'll show you in a moment, we've binned them. So you'll see, so they represent sort of all the releases conducted in the range indicated on the axis. And then the vertical axis here represents the proportion of releases that are detected in each bin. So what the data looks like, this is again a sample data from one of our tests, just to give you an example. So here, each bar represents the portion of the releases that we conducted that the aircraft we were testing was able to detect. So in sort of the bins on the right, everything from 15 and above, they were able to see 100% of the releases we gave them. The little tick marks at the top and bottom of the axes represent the individual measurements, and it's at a 1 if they detected it, at a 0 if not. And so sort of on the left half of the axis, you can see this is where they begin to miss some of the smaller releases. So we gave this aircraft sort of 47, quite a lot of releases below 5 kilograms per hour, and they saw 4 of them. We gave them sort of 22 between 5 and 10, and they saw 16. So you can get a sense for where their capabilities begin to drop off. So across all of the tests we conducted, we have evaluated the performance of 6 different aircrafts. These use passive spectroscopy, active spectroscopy, and in situ measurement techniques, the 3 approaches I described. It sounds like someone's unmuted. Chris, maybe you could mute the person who's unmuted. Thanks. So for the passive spectroscopy approaches, we had sort of these 4 different test participants. So Carbon Mapper, GHGSat, Kairos Aerospace, and methane-sat, which is the aircraft, or methane-air, which is the aircraft precursor to methane-sat. And these all use that passive spectroscopy approach relying on reflected sunlight. Active spectroscopy, we tested Bridger Photonics, and they use that LiDAR approach. And then we also tested scientific aviation, which uses in situ measurement. So the results from all of these tests are included in the papers at the bottom of this slide. All right, so I will dive into the results now. And so I'll just sort of walk you through what we found for each one of these different operators. So first, Carbon Mapper. A bit of context, Carbon Mapper, it's a nonprofit organization. It's based on the US. They're largely supported by philanthropy, but also offer commercial leak detection services as well. So we found quite strong performance in their quantification abilities on the parity plot on the sort of the left plot on this slide. And in terms of their detection capabilities on the right plot, they were able to see every release that we gave them that was above 10 kilograms per hour. And so the smallest measurement that they were able to conduct with us was around 11 kilograms per hour. This is GHGSat. So they're a private Canadian-based company, and they're commercial. They offer methane leak detection services, both for their aircraft platform as well as their satellite, which I'll be showing in the satellite portion of the results. And again, we see very sort of strong quantification performance in their parity plot, and we see they're quite close to X equals Y as well. And they were able to see smaller releases than Carbon Mapper. The smallest measurement they detected was 3 kilograms per hour, although they weren't able to do that consistently. And then they generally saw everything again above 10 kilograms per hour. Kairos Aerospace is a US-based commercial company. Again, they also offer commercial methane detection services, and they use passive infrared spectroscopy. We tested Kairos Aerospace twice, once in 2019, in Sherwin et al. 2021. That's sort of the paper that summarizes the results that's really just focused on Kairos, actually. That was one of our early tests, and we only tested them. And then we also tested them again this past year in our Arizona Fall 2022 campaign, and those results are going to be included in my upcoming paper, in which we tested 5 different airplanes. So across these 2 tests, we had 2 different altitudes that they were operating at, sort of 900 meters above ground level and 450 meters above ground level. And we saw really consistent quantification performance in both of these scenarios. On the next plot, I'll show the 2 different tests, the detection capabilities. And here is where we see that the lower altitude, the lower flight altitude resulted in much greater sensitivity to detecting smaller releases. And the smallest release they detected with this configuration was 3 kilograms per hour. And they were quite consistently able to see small releases. They saw everything above 10 again, but really sort of in the 5 to 10 range, we're able to see quite a lot, as you can see from this plot, which is an improvement over our testing in 2019, where they saw everything above 15, and then that really tailed off, and they were barely able to see. Of the 14 releases we gave them between 5 and 10, they saw 1. So this shows really the effective flight configuration. And then finally, the last aircraft that we've tested, or the last aircraft that we've tested that uses passive IR spectroscopy is Methane Air. And so this is a nonprofit organization. They are the Environmental Defense Fund's precursor to methane-sat. So it's using the same technology that they will soon sort of launch in their upcoming satellite. This technology is designed more for diffuse sources, not just point sources. And so as a result, they have a higher, lower detection limit. The smallest thing that they were able to see that we conducted for them was 34 kilograms per hour. We see very strong accuracy in their quantification estimates. Bridger Photonics uses a LiDAR mapping system. So that's the active spectroscopy approach that I discussed earlier. And the testing we conducted with them was in 2021 and in collaboration with the Colorado-based METEC, another organization that conducts methane tests at even lower release rates than we do. Bridger is a private US-based company, and they also offer commercial methane detection services. And so here the figures I'm sharing are from work written by Clay Bell, who was at METEC at the time. And so here, we see, again, strong quantification performance, consistent. This is really sort of a theme across all of the aircraft platforms we tested. The LiDAR approach, however, the difference here that we see compared to the passive spectroscopy approaches is that this allowed sort of very high sensitivity to smaller releases. And so the work here tested two different flight heights at 150 and 205 meters above ground level. And the smallest measurement that was observed was 0.17 kilograms per hour. So this is actually several orders of magnitude smaller than what we're seeing with some of the other aircraft technologies. And finally, the last aircraft that we tested was Scientific Aviation. This company uses an in situ measurement approach. So they measure the downstream concentration, the downwind concentration, again, that I sort of described at the top of the presentation. They're a private US-based company. And the measurements sort of take a bit longer to conduct, which is why you see fewer data points on this plot. However, in addition to measuring methane, they can also measure with the configuration that we tested, ethane, carbon dioxide, as well as water. So we see sort of, again, quite strong performance, a bit of a downward trend in the slope, but I think that's an artifact of having fewer data points. It's a bit hard to tell. We would need to conduct a few more studies with them. So the results of our aircraft studies are summarized in several different papers that I've included here on this slide. Evan Sherwin and Yulia Chen wrote up our evaluation in 2019 of Kairos aerospace performance. Clay Bell wrote up the work on testing Bridger, that's evaluating the aircraft-based LiDAR system. And then Jeffrey Rutherford and I both wrote papers that are currently in the peer review process, but we have posted preprints. And again, the link to those preprints can be found at this URL. So this sort of wraps up the aircraft portion of our results and brings us to the satellites. So before we dive into the satellites, here, as I said, sort of previously, we're measuring methane, not just sort of above ground level, but through the entire atmosphere. And so you can expect to have higher detection limits and greater uncertainty as well in the measurements that you'll see. There are two different types of satellites that we tested. There are satellites that have global coverage. So these satellites, based on sort of their orbit and their altitude above ground level, can see the entire planet, the entire globe, but they have, as a result, lower resolution. The other type of satellite that we tested is called a tasked satellite. So here, the satellite in its orbit will actually point at a specific target. And this allows for higher resolution, but at the cost of that global spatial coverage. But you'll see that sort of the tasked satellites are able to see much smaller leaks than the ones that have global coverage. So here are all of the satellites that we've tested across 2 years of testing. The global coverage satellites are Landsat 8 and Sentinel-2. When I show you the results, I'll share a bit of more context on those, on each specific satellite. And then here are the task satellites. And these can sort of further be divided into those that are government operated and commercially operated. So all of the satellites in the top half of the slide are government operated satellites, and the GHGSat and Worldview 3 are both commercial satellites. And then again, as I mentioned in my introduction, the data from all of these satellites, we distribute it and it's analyzed amongst different teams. So we have academic, commercial, as well as government teams analyzing the data that we collect. For each satellite, while the satellite sort of passes over our release point at an instantaneous sort of moment, we conduct a 20-minute long sustained release. So this is 15 minutes before the satellite is overhead and 5 minutes after. So due to the sort of both sort of that longer length of time that we're conducting the release, as well as the infrequent revisit times, we do have a smaller sample size. So we're able to see sort of trends across all satellites in aggregate, but I'll share with you the results for each individual satellite. But bear in mind that you're going to see only a handful of data points. And in some case, for satellites, we were very happy to get even in a single measurement, because at times tasking the satellite requires a lot of logistical planning. So I'll begin with the global coverage satellites. Landsat 8. So this is a satellite operated by NASA and the USGS, United States USGS Geological Survey. All data from this satellite is publicly available. It provides global coverage every 16 days. And so here we conducted tests in 2021 and in 2022 with Landsat 8. So, you know, just a reminder here on these images, we've switched units from kilograms per hour to tons per hour. And you can see in our 2021 tests, we were conducting from it's sort of up to, as I said before, we're capable of releasing up to 7 tons per hour. The x-axis on our tests from 2022, we had a sort of smaller dynamic range for those tests, and we were able to conduct releases up until about 2 kilograms per hour. And so the smallest measurement we were able to conduct with Landsat 8 was about just under 1.5 tons per hour. And sort of that was in 2022. And I'll point out on this plot, the non-detect, so that's where an analysis team looked at the image and was unable to see methane, are depicted sort of in this bottom bar on the right axis. And so you can see we conducted releases below 1.4 tons per hour that the teams did not observe. So that's what those dots across the bottom represent. Here are our results for Sentinel-2, another satellite that we were able to test for the higher volumes in 2021, where really this satellite was able to see quite accurately. We managed to collect quite a lot of data across sort of in the 2021 test across the range of 1 ton to 7 tons per hour. And then in our 2022 testing, we conducted many releases sort of around that detection limit. And the smallest release that we observed was 1.1 tons per hour. And just a little bit of context on this satellite, Sentinel-2. This is a European Union operated satellite as part of their Copernicus program. And it provides global coverage again, and it revisits sort of 2 to 3 days in mid-latitudes and has a revisit time of 5 days at the equator. All data from Sentinel-2, again, is publicly available, and it's used in a number of scientific studies. We also tested Nmap, so now we're moving into the task satellites. So this is a satellite launched very recently by the German Space Agency and the German Research Center for Geosciences. It's a tasked satellite. The data is available publicly, but tasking sort of is conducted upon request. So requesting the satellite to look at a specific location. And so we were able to conduct one measurement with Nmap. And here our sole release that we conducted was 1.1 tons per hour, which was seen, which it was able to see. We also tested for the first time this year in 2022. We were really excited to be able to test 2 Chinese satellites. Gaofen 5 and Ziwan 1. And both of these, we again had a limited number of, these are both tasked satellites. We worked with our partners at Nanjing University to obtain the data from the satellites, which can be made available upon request. And here we saw both satellites were able to see around 1 ton per hour. But again, this was the first time we were able to evaluate these satellites. So we don't yet have the data to really see how low that might go. GHGSat is a tasked satellite that's operated by a private Canadian company. So again, this is the same company that operates the aircraft GHGSat AV, the results of which I showed earlier. And as with their aircraft, GHGSat also offers commercial services for methane leak detection. This is a tasked satellite, and then so you can pay for commercial services to task the satellite above specific locations, but also tasking and data archives are available for scientific proposals to GHGSat. So we were able to collect a few data points for GHGSat across our 2021 and 2022 tests. And the smallest measurement that we conducted with them was 0.2 tons per hour. So quite low compared to the 1 ton per hour that we were seeing for the previous satellites that I shared. So this shows how some of the satellites really, with tasking, can achieve quite low detection limits. Prisma is a satellite operated by the Italian Space Agency. Again, it's a tasked satellite. Tasking can be conducted upon request, and then the data is made publicly available. And so we were able to collect a handful of data points, both in our 2021 and 2022 testing, and the smallest measurement that was observed using Prisma was about 0.4 tons per hour. And finally, Worldview 3. So this is a satellite operated by a private US-based company, Maxar. Again, it's a tasked satellite with very high resolution, and it operates commercially. Again, tasking sort of as with the commercial satellites that we've seen so far, tasking and data archives are available for select proposals. And so we actually worked with them to provide data to all of our analysis teams in the 2022 tests we conducted, where we were able to collect a number of data points depicted on the image on the right of the slide. And they were able to see this, the smallest measurement they conducted was 0.03 tons per hour, 30 kilograms per hour, which is quite impressive. So incredibly low. The results from all of our satellite tests are available in work that was written up by my colleague, Dr. Evan Sherwin, in 2 papers, one that is published. The 2021 results are published in Scientific Reports, and the 2022 results are in the peer review process, and a preprint is posted at the URL that I've provided for all of you. And these images are from the paper, and they sort of show all of the points from all the satellites sort of on the same plot. And I'll just point out that, you can see, while the error bars may be sort of quite large in some of these cases, that overall these satellites are in aggregate quite accurate. They're giving us quite a good, they can give us quite a good sense of how large a methane release is. So to summarize my talk today, we began by discussing how aircraft and satellites measure methane. I walked you through how we at Stanford conduct independent testing to evaluate aircraft and satellite methane measurement capabilities. And finally, I shared with you the results from our tests. And sort of overall, aircrafts and satellites really are in a position to allow us to rapidly find and fix methane leaks coming from oil and gas. And I think that they are that's kind of the synthesis takeaway of the work we've conducted over the last several years. The key takeaways that I really want to share with you today, we see that the aircraft-based technologies can have very high accuracy in sensing methane emissions. And we find that in our studies, they can detect releases as low as, depending on the platform, 2 to perhaps 10, maybe higher kilograms per hour. Satellites on a whole can see sort of larger emissions. Oftentimes we'll see ranges between 0.1 to 1 ton per hour, but the targeted satellites can see smaller emissions. And so while our studies really represent ideal measurement conditions, we find that these technologies are ready for use, and that it's time that sort of we use them to find and fix methane leaks. I'd like to, before I open it up to questions, I would like to thank the myriad of people who were involved in this work. This includes sort of Professor Adam Brandt, who's been leading this effort over the past several years, as well as several PhD students, past and present: Philippine Bordeaux, Richard Chen, Yuanlei Chen, Jeff Rutherford, and Jan Zhang. And then sort of I led our most recent campaign of testing in this past fall, and then Evan Sherwin led sort of the 2021 testing, and he's a postdoctoral researcher also at Stanford. And finally, just I need to acknowledge our funding sources. These are incredibly expensive experiments to conduct. We sort of are operating a lot of equipment. We work with contractors. And so I want to thank the funders for our fall 2021 campaign. So this work was supported by the United Nations International Methane Emissions Observatory, as well as the Environmental Defense Fund, Global Methane Hub, and the Stanford Natural Gas Initiative. And we really have sort of indispensable partners in the field: Rawhide, who operates our natural gas equipment. And we work with Volta Fabrication very closely on designing our gas metering skid and the equipment that we use in the field.